Hey everyone, so today I'm going to be telling you about changing of momentum, which is also known as impulse. So whenever you're trying to calculate change in momentum, you can do the final momentum or minus the initial momentum, and that's going to be equal to a number. And as you know, if momentum is conserved, that's equal to 0. Now, change in momentum is also the same as doing the calculation of force times acting time. So impulse or change in momentum can also be calculated by measuring or multiplying the force applied to an object times the time that that force was acted or was acting on that object. So force comes in newtons and time comes in seconds. So change in momentum has the units of Newton seconds, or because it's still momentum, kilograms meters per second. And this comes because force also has the units of kilograms meters per second squared. So if I get kilograms meters per second squared times second, I get kilograms meters per second. Okay? Now, because change of momentum is force times acting time, what can I do to get the same change of momentum? Well, I can play around either with the force or the acting time, or both really. So look at this picture. So here I have that I just got randomly from the internet. So here I have for the same change in momentum, so the big and the small you get to know from the size of the letters. So change of momentum has the same number, same height of the letters in the two of the pictures. So change of momentum will be the same for a long time and a small force, or a big force over a short time. So if I apply an amount of force into a person, but I take a long time to apply that force, then the change of momentum is the same, but the force that the person feels is not very high. On the other hand, if I do a quick punch, like in this picture, I can get the same change of momentum because my time was small, but this time the force was big. So if I'm increasing one of the numbers that I'm multiplying, overall this number increases. But if I decrease the other number, so one increases and the other decreases, this number can stay the same. So I can get a big impact, a big force on if I getting by the same change of momentum, but making the acting time to be small. And this is how it works in box actually, and in other sports. If you want to apply a big force, you need to make it into a very small time, the contact time. So the momentum that you apply is still the same, but the force acting on the others is bigger. The opposite works for safety or car safety. You have seat belts to increase the acting time, or the air brakes as well to increase the acting time, where the force of the impact is going to be acting on you. I have a video about car safety that is coming, I suppose is the next one. So in order to get the same change of momentum, I can get a larger force for a short time or a smaller force for a long time, okay? So let's apply this. Let's look at an exercise. This one is from AQA. So a bullet of mass 0.004 kilograms moving at a velocity of 90 meters per second is stopped by a bulletproof vest in 0.0003 seconds. Calculate the deceleration and then the impact force. Now, deceleration is change in speed over time. So I have a change in speed from 90 to 0 in the time of 0.003 seconds. So final velocity is 90 minus initial velocity, that is going to be 0, so that's minus 90 meters per second. Final velocity was 0, sorry, minus 90 meters per second divided by the time taken. And this gives me a deceleration of minus 300,000 meters per second squared. The minus sign shows that I have deceleration, okay? That my velocity was decreasing. Now, the impact force. Well, I know that force equals mass times acceleration. I can actually use that formula, and I can then get that the impact force is going to be 0.004 kilograms times minus 300,000 meters per second squared. This gives me an impact force of minus 1,200 newtons. My change in momentum, they don't ask, it would be this force times 0.0003. This would give me the change in momentum. And when they say calculate the impact force if the time had been 0.0002, you will see that because it was a faster impact, the force would be bigger. Okay, the deceleration would be larger, therefore mass times acceleration would have a bigger number. Okay, so this exercise actually doesn't show as much as the change of momentum equals force times impact acting time, but you will have that coming up in another video. Now, something else. So I've been telling you about how fast these things can decelerate, and I have a video here of a golf ball hitting a steel in a super slow motion, and so it's about 1,000 or more than 1,000 frames per second, and you will see that objects decelerate very fast, but they are still there is still an acting time. So this, for example, the bullet, it's not stopped instantaneously. The golf ball is not stopped instantaneously. So this is where you use the formula impulse equals change of momentum, impulse or change of momentum, which is equal to force times acting time. Okay, so that is it for today in terms of impulse. I'm going to apply this to car safety in the next video, so it was just for you to get to know the formula, how it works, and then we are going to apply it in another video. Okay, so up to my next video. Be happy and healthy. Bye.